Good morning. So in yesterday's video, we looked at sort of GCSE proof and then proof by deduction. And this is basically using algebra to prove statements. And so this one I've got here at the beginning of today's lesson looks a bit like one of the ones from yesterday. And if you had a go at the two from yesterday's lesson, one of them was a bit like this, and it was several of them had gone this way. So I squared both sides. I collected everything on the left-hand side and found that that gave me something I could factorise as a perfect square. And we know that anything squared is greater than 0. So it looks like this one is probably going to go that way. So let's do my rough working. So I will expand the left-hand side and add 20 to both sides. So I've got that, and then I just hope that that's going to factorise into a perfect square. It doesn't. I can't factorise this as something squared. How am I going to prove that it is greater than or equal to 0? Well, we use completing the square. So pause at this point and just see if you can complete the square for that expression. Well, okay, if your completing the square skills are a bit rusty, rest assured, so are mine. But yeah, I think I've got there eventually. So I've completed the square for this one. And the way you go from here, you could go in a couple of ways. So I could, at this point, say, right, I am going to take away 4 from both sides. And I know that that's true, because I know that this is always going to be positive. So that's one way of doing it. The other way of doing it is to say, well, I'll do it graphically. I know that if I was to plot y equals this, its turning point would be, well, that's being moved forwards 4 and up 4. So as a quadratic, it would look like this. Now, I know it's n's and not y's and x's, but you could use a graphical solution to explain why this is always above 0. I think this way is a bit safer, to be honest. So my solution, therefore, I just run that in reverse. So I say, okay, n plus 4 squared is always greater than minus 4. Has to be. This is always going to be 0 or bigger, so it has to be bigger than or equal to minus 4. And then add 4 to both sides. Expand that to show that you get what we were after as required. So don't panic in your rough working. You get to a point where you're expecting to be able to square it here, to factorise it as a perfect square, and you can't. Instead, complete the square, and then the process is very similar to the one before. I'll give you one of those to try in just a moment. But here's the second sort of problem I wanted to talk about before we left proof by deduction. Here's one where you've just got to show that something on the left-hand side equals something on the right-hand side. Now, they're all like that, but this is very definitely an equal sign rather than a greater than or equal sign. And in fact, it's the triple equal sign, which you may remember means an identity. It means it's always true. Now, this sort of proof question crops up a lot in trigonometry, where you're trying to prove one of those trig identities that we use, and you've met a couple so far. Tan is sine over cos, and sine squared plus cos squared equals 1. But there's a whole load of them that we meet in year 2. So with this sort of statement, and nearly always they'll put a triple equal sign in to show it's an identity, you are okay just locking one side and making the other side look like it. So I'm going to lock the left-hand side. I'm going to leave it alone, and I'm just going to consider the right-hand side. So I'm going to expand the right-hand side. So I'm going to multiply those two brackets out, and then whatever answer I get, I'm going to then multiply by that bracket. Except you're going to do that for me. So go on, pause, and have a go. So when I gridded out the first two brackets, I got x squared minus x minus 20. So I put that here and multiplied it by the final bracket, 2x plus 3, and gridded it out. And then it's always stripy, isn't it? So you've got your x cubed, so there's just one x cubed term, 2x cubed. I've then got a minus 2x squared and a plus 3x squared, which gives me plus 1x squared. I've got a minus 40x and a minus 3x, that's where the minus 43x comes from, and the minus 60, which is what the left-hand side equals. So that's proving an identity, which is a bit more straightforward than the other proof by deduction questions we have done. Okay, 2 for you to try. Have a go, and I'll show the answers in a minute. So here you go, looking at this one, it is already greater than or equal to 0, so if that became a nice perfect square I'd be happy, but it doesn't, so I complete the square and do that, and then running it in reverse just to formally write the solution. And remember I said in the last video, to be honest, you're probably okay if you do it that way. This is just sort of doing it properly. And then this one, I spotted it was an identity, so I was okay just leaving the left-hand side and working on the right-hand side. It's not always the right-hand side. Sometimes you leave the right-hand side and just work on the left-hand side. So that squared, I multiplied out. X times b over 2, I wrote as xb over 2. You'll see that's slightly foolish when you look at what I've got to make it look like, but anyway, never mind. B over 2 times b over 2 is b squared over 4. Which is the same as the second part of the statement, b over 2 squared, so that's b times b, and 2 times 2 is b squared over 4. So here you've got a half of xb, and here you've got another half of xb. Add those together, you get a whole xb. And the b squared over 4 gets cancelled out by that one there. So you end up with this. Now, even though they wrote it that way, we all understand it's the same thing. xb, bx is the same thing, so all good. Now, proof by deduction is the gold standard, if you like, of proof. You're not trying actual values, you are demonstrating something using algebra. But there are two methods of proof on the A-level syllabus which involve just trying numbers. And the first of those is proof by exhaustion. Now, how can you tell that a question is a proof by exhaustion question rather than a proof by deduction question? Because we have looked at questions about two consecutive square numbers and we've done them using proof by deduction. Well, it's because normally you can tell that there's only a limited number of options, and in this case we are told that we're only dealing with the square numbers from 1 squared to 8 squared. So we've got to prove the sum of two consecutive square numbers, so next to each other, is an odd number. So that can only be 1 squared plus 2 squared, 2 squared plus 3 squared, 3 squared plus 4 squared, you get the hang of this, 4 squared plus 5 squared, 5 squared plus 6 squared, 6 squared plus 7 squared, 7 squared plus 8 squared. So I will work all those out. So that's 1 plus 4, so that's 5. That's 4 plus 9, so that's 13. That's 9 plus 16, which is 25. That's 16 plus 25, which is 41. That's 25 plus 36. You get the hang of it. 36, sorry, equals 36 plus 49 equals 49 plus 64. So you've tried all the possibilities and they've all come up with an odd total as required. So proof by exhaustion is just you try every possible combination, and you wouldn't be expected to do a proof by exhaustion question with 400 examples to try, but here we just had 1, 2, 3, 4, 5, 6, 7, perfectly reasonable. So have a go at a second proof by exhaustion question. Pause and have a go. Only 4 possibilities. We were talking about consecutive positive odd numbers less than 10. So that was only 1, 3, 5, 7 and 9. So these were the only combinations. They were all even, so we have proved it by exhaustion. Always that simple? Sadly not. Let's look at a couple of trickier examples. So again, I'm going to ask that same question. How do I know that this is a proof by exhaustion question? Well, our proof by deduction methods wouldn't help us in this situation. But if instead we think about what sort of numbers could x be? We know it's an integer, but what sort of numbers could it be? And also there's a bit of a clue in that we're told it's an odd integer. So what I'm going to do now is, rather than trying specific numbers, I'm going to say, right, okay, let x be even. I'm going to try it that way. And then I'm going to try let x be odd. Okay? So in this one, an even number is 2n. So I'm going to substitute 2n into there. So I'm going to get, right, 2n cubed plus 2n plus 1. So I've replaced x with 2n. If x is odd, remember how we write odd numbers? Either 2n plus 1 or 2n minus 1. So I'm going to I'm going to substitute 2n plus 1 in there. So I get 2n plus 1 cubed plus 2n plus 1 plus 1. And hopefully, in both cases, I'm going to be able to demonstrate that my answer is an odd integer. Have a go. This one's quite straightforward. You've just got to multiply that out. Here you've got to multiply that out, which is a sort of grid it out twice. But hopefully you can then go on to demonstrate why each of them has to be an odd integer. So here's how I've done it. So the first one, when x was even, was quite easy. 2n cubed, remember, it's not just 2n cubed, it's 2n times 2n times 2n, so it's 8n cubed. So I got this. Now, for that to be odd, I just chose to prove that it was one more than an even number. So how do you prove something is even? Well, you show that you can write it as 2 times something. So I factorised that as that. So I know that is an even number. Add 1 to it, has to be an odd number. This one was a bit more complicated. So 2n plus 1 cubed, I did 2n plus 1 times 2n plus 1, which gave me 4n squared plus 4n plus 1, which I then multiplied by 2n plus 1 again. Got that. That gave me 8n cubed plus 12n squared plus 6n plus 1. Nearly forgot the plus 1, just squeezed it in there. So that gave me that. You've then got your plus 2n plus 1 still there. So if you simplify all that, you've got your 8n cubed, your 12n squared, you've got 6n and 2n, which gives you 8n, and then you've got a 1, a 1 and a 1, which gives you 3. Similar proof. Think of this as plus 2 plus 1. So you can factorise it as 2 lots of that. I know you can pull out a 4, but I'm only using this to show that it's an even number. This is an even number, so I pull out the 2. So that's an even number, so adding 1 must give you an odd number. And so I've proved it for both even and odd, so I've done a final sentence there, adding in the whole integer thing as well. Here's a rare and beautiful thing, a proof by exhaustion question that tells you it's a proof by exhaustion question. Very rare. So 3 consecutive integers, we've got to multiply them together and show that we always get an even number. Proof by exhaustion. What are the different options when you've got 3 consecutive numbers? Well, you could have an even number to start with, couldn't you? So that would be even, odd, even. So if the first number's even, then I would call that 2n, and then the next one would be 2n plus 1, and the next one would be 2n plus 2. So that's one option. So if we're dealing with an even, odd, even combination. And then the other option is that the first number's odd. in which case my first number is 2n plus 1, and then I've got 2n plus 2, and then I've got 2n plus 3. Now we're finding the product, so we're multiplying those together. So go on, expand those brackets. Remember, do it by multiplying out those two and then taking your answer and multiplying it by that, and multiply out those two, taking your answer and multiplying it by that, and then see if you can convince me that the thing you get is even. So if we're dealing with an even followed by an odd followed by an even, we get that combination, finding the product, and we're multiplying. I could do that in my head. So that's just 4n squared plus 2n. So those two give me that. I then need to multiply it by 2n plus 2, so I gridded that out. Gave me this. Now I know I can factorise that by playing out of 4, but I only want to demonstrate it's even, so I write it as 2 times something. 2 times anything will always be even. This one was a bit trickier, so I multiplied my first two brackets together. That gave me 4n squared plus 6n plus 2, and then multiplied the result by 2n plus 3. Gridded it all out. That gave me this. I was then able to write that as 2 times something, which must be even. So I've coped with the two different scenarios, hence whatever you get, the product of 3 consecutive integers is, not also, always even. Okay, one for you. This from the 2019 AS maths paper. Given that n is a member of the set of natural numbers, so that basically means natural numbers are positive integers. So it means given that n is a positive integer, prove that n cubed plus 2 is not divisible by 8. Classic proof by exhaustion question. So basically, let's consider even. So let's replace n with 2n would be a bit confusing because we've already got n, so I'm going to replace it with 2x. See what you get when you multiply that out. And odd, so let's replace n with 2x plus 1. See what you get. Can you prove it's not divisible by 8, not a multiple of 8? And I'm not going to go through that in the video. I'm going to post a work solution to that. So that's the end of the video once you've had a go at that one. And then next week we will move on to the second sort of proof where you actually get to try numbers. Take care.